during the lecture, whenever you feel like asking a question or adding your opinion, please feel free to do that. You can just raise your hand. And today, like, I don't have the candies like Pascal and Chris, but I hope that you will care to ask questions or answer the questions. Okay, so this is the outline of today's session: graphical modeling, Bayesian networks, causal modeling, and then at the end we'll have discussion about graphical modeling and deep learning, where you can also join. The sound is okay at the back? Okay, so first let's do some like a warm-up recap session. I'll be showing some words, so you can just like think about the words, what they mean, and how they relate to the other words. Model, data, parameters, real world. So does anybody want to say about those words? Definition or relationship or whatever? Okay, so, and uncertainty, complexity, likelihood, and modularity. Anyone? Okay. Similarly, like inference, prediction, because those are the words that we learned in our past 10 days, right? So whatever your impression, it need not be any very formal definition. Whatever you feel like saying, you know, like the difference, the relationship, or whatever. Inference, prediction, transformation, minimization, maximization, optimization. Anyone from the front row or back? Okay. Is it too early for people to speak? Okay, we'll have more question-answer session. So similarly, like the probability statistics, distribution association, Bayesian, correlation, regression. I mean, I think you all are familiar with those words, right? Because those words will keep on appearing in the ongoing slides. Okay, so this is just like a simple warm-up session. So the point I was trying to make is like all these words and concepts and constructs that you learned from books and your lab session or whatever. So I really encourage you to, like, from the books and from those tutorials, put on your own like conceptual table and play with them like you play with the Lego. So this is just the education researcher in me, like trying to give you some advice. Okay, so now we'll start with graphical models. Let's start with some examples. This is a graphical model. It's a toy example. And this is another very like a famous toy example for graphical model. And this is the graphical model used in health analytics. This is an intelligent tutoring system. Also, by the way, during the session, I'll be giving the examples from education. One thing I noticed, like during the Sujay and Pascal session, where the group were supposed to talk about what they want to do with AI, and I didn't hear anybody was interested in AI in education. So, oh, you did? Oh, sorry, my bad. Okay, because this AI in education is a very like active research area. So one of the goals of my today's session is like make you kind of curious or interested in AI in education as well. Because when I'm giving example from this particular domain, if you don't understand particular terminology, again, please feel free to raise your hand and ask. So this, again, another intelligent tutoring graphical model from ITS. This is also another graphical model. And this is from natural language processing. I think you saw some from Suresh sir's presentation. And this is from recommendation system. Okay, so now we'll go to some definitions. So graphical model consists of a graph structure. Each node of the graph is associated with a random variable, and the edges in the graph are used to encode relations between the random variables. There's a graph and there's a relationship. And graphical models are a marriage between probability theory and graph theory. And this is another definition. Graphical models comprise any model that uses the language of graphs to facilitate the representation and resolution of complex problems that use probability as representation of uncertainty. And this is the fourth definition. Graphical models are an elegant framework which combines uncertainty, probabilities, and logical structures in the form of independence constraints to compactly represent complex real-world phenomena. And again, I highly recommend all of you to read those definitions and create your own definition that personally resonates with you. Okay, so before starting, like again, this is a little bit of the advertisement of graphical models. So what do they offer, right? So there are a lot of texts, so please bear with me for a while. We'll go to the graphs after that. So they provide actually, they give you tools to deal with uncertainty and complexity, which are the major AI problems. So we deal uncertainty with probability theory and complexity with graph theory. So basically, it adds the concept of modularity. So because the real world is so messy, the variables everywhere, right? So you try to make them like more simpler, more tangible, more modular with the graphical models. Again, so I really like this, because it provides you a way to represent the formalism. So what it helps is because there's a different domain, different data, right? So when you have the graphical model, you can actually transfer this model from one domain to another, one data source to another. And the cool thing is also it gives you the way to design new systems. So it's really good for like exploration and creativity and new experiments. So the three components of intelligent system: representation, inference, and learning. So graphical models have these capabilities to encompass all this. So by this, I'm not saying that like graphical models can do everything, but they, as a structure, as a approach, have a lot of affordances. So the point is like graphical models are all encompassing. You can use in very different domains, like we see in health, education, recommendation system, control system, all that. And actually, they are very intuitive and they are rigorous. They bring the best of the both worlds. So the point is like graphical models are awesome and I love them. Okay, so I'll take you back to the definition number 2. So graphical models are a marriage between probability and graph theory. And I think most of you are from, you know those theories. So what does graph theory does? It's actually that the intuition comes from the graph theory. It brings you this structure which can be highly interacting set of variables. So it feels very tangible. And the probability brings the glue, like it's not just, oh, the variables are connected, right? How are they connected, or how they are not connected, or how are they conditional connected? So those things are brought by the probability theory. So first I want to settle this. So like how much graph theory is there in graphical modeling? So up to my knowledge, not really. Like as long as you know the vertex and A's and direct and undirected, you are fine. So you don't have to think about all these other complex graph theories, this max flow, mean cut theorems. And somebody said that like if you are good at probability but not graph, whatever. So the thing is like in graphical models, so probability theory is more involved. So now let's go to probability. Again, this will be some like revision of the concept that you have learned in the last sessions. So there's joint probability and conditional probability. So joint probability is the measure that two events occur at the same time. Like, what is the probability of picking a part that is both red and 6? And conditional is the measure that one event will happen given that the other action or event happens. So the probability that you get a 6 given that you drew a red card. So anybody wants to give their own examples? Okay. So maybe after the tea break, I'll be hearing more response from the audience. So again, this dependence and independence, right? So dependence is like when one event influences another. For example, you have traveled to Kathmandu. So suffering from allergy, they are dependent events. It increases your chances that you might suffer from allergy. And the independent events are like they don't have connection. Like you travel to Kathmandu and meteor falling on the Jupiter, they have no connection, unless you believe in astronomy. So, and there's, again, like, continue that, there's the independence and conditional independence. And I think this concept is very crucial, so which will be dealing more and more in the further slides. So the independence is like the two depends are just independent, right? They don't have any relationship. And the conditional independence is like those two events, they might be dependent if you just look at the two events, but given that the other event has happened, they don't are dependent. For example, this, okay, so you have the knowledge, right? You have the grades, but if you take out the okay, I'll give you a better example later. Okay, so now back to graphical models. So they are basically, there are like tons of different graphical models, but in the scope of this session, we'll be mentioning two major graphical models. One is undirected and one is directed. Undirected graphical models are called Markov networks, and the directed graphical models are called Bayesian networks. And this Markov word appear again and again at different contexts, so don't get confused. So undirected graphical models are like Markov networks. So they are mostly used, more popular with physics and vision communities, and directed models, Bayesian networks are more popular with AI and statistics. So in this session, we'll be talking more about the Bayesian networks. Okay. So the Bayesian network is a directed acyclic graph in which each node corresponds to a conditional dependency and each node corresponds to a unique random variable. And Bayesian networks use Bayesian inference for probability computation. Basically, Bayesian networks are the graphical models with node and edges where the edges have directions. And all these edges have meaning, like the direction and the node, everything has meaning. The probabilistic significance. So in Bayesian network, we'll be talking, so there is like a representation, how Bayesian network represents the model, or how you can represent Bayesian network. And there's like how you can do inference in Bayesian network, and how you can do learning in Bayesian network. So the Bayesian network concept, two parts. So one is the qualitative part, again that is the graphical part, and one is the quantitative part. So this is one example. So there is the knowledge and there's the performing correct. Those are two variables. So those two are distinct variables, right? Having the knowledge and performing correct, they are like related, but they are different variables. And so these are called conditional probability tables. They actually show you the joint probability distribution. You might get confused a little bit, but like knowledge, so that is the conditional probability table for the knowledge, and this is the conditional probability table for the performing correct. And because this is dependent on knowledge, so you are going to have this two-dimensional conditional probability table. So as I said, like this graph is the qualitative part, and these conditional probability tables are the quantitative part. So how many of you know this conditional probability table? Okay. So at first it might seem a little bit, like all this graph, which is related to what? But I think the further examples will make it clear. This is very like simple concept. Just this this table makes it confusing. Okay, so the quantitative part, right? So I have just put the variables, but how are you going to fill those variables? Like you can get the graph from your common sense, right? You know that knowledge is going to affect perform correct, but you don't know how much. Like what is the probability distribution of knowledge, or what is the probability distribution of perform correct? So this is, I just put it like random number here. Like let's say the probability that you know knowledge is like 50%. I just plug in those numbers, and okay, how about this? Like in the ideal condition, right? So this says like, so this is for this, and this is for this. Everybody clear? Is it some confusing? Like which relates to what? So this says that, like, if your knowledge is true, what is the probability that you perform correct? If you have the knowledge, it should be 1, right? And if you have the knowledge is true, then performing correct is 0. And if you have the knowledge false, like if you don't know the knowledge, the probability that you get it correct is 0. And if you don't have the knowledge, the probability that you don't get it correct is 1. But this is the ideal situation. And in real world, there will be like guessing and slipping. Because sometimes you know in your head, but you slip and you can't get it correct. I think it has happened to everyone. And sometimes like you don't know the answer, but you can still guess, right? I mean, if there's multiple choice, you can guess or you can cheat or whatever, you know. Like even if you don't know the knowledge, you can still get it correct. So the thing is, like, if you have the knowledge, there is like a 80% chance you get it correct, you perform correct. And if you have the knowledge, there is a 20% chance that you still get it wrong. Means like 20% chance of slipping. And if you don't have the knowledge, there is still like 30% chance that you get it correct. There's a 30% chance of guessing. So can you guess, like, if there are 4 multiple choice, what would be the value? 0.25, right? And if there are 2 multiple choice, and if there's only 1 choice? 1, okay. So this is how it goes. Okay, now we are going to, the thing is like, so this is just a model. You can apply it to different worlds, you know. So let's say like you apply this model to this one model student A. So she has very high knowledge, but she's very careless. Who resonates with this model? Who among you think that you have high knowledge, but you are very careless? Okay, so this is your model. So if you look at it, there's a probability that you have knowledge 0.9. So you know it 90%, right? But there is 10% chance that you don't know because you have high knowledge, but you don't have perfect knowledge. Here is like, okay, so even if you have high knowledge, you only get it 60% right. So 40% time, you know, you slip, you know, because you are careless. Similarly, like, let's say you are this another student, you have low knowledge, but you are very clever at guessing. Who relates with that? Who do they think is this? Or anyone you remember who is like that? They don't know, but they just can't guess it. Okay, so they only have the 30% chance of knowing, right? But still, you know, they are so good at guessing, they still get it 60% correct. Similarly, you can apply this model not only for students, but also for the tutor. So this is, you know, like, again, back to the concept of like a model and real world, you know. So you can model a student, you can model a tutor, you can model a classroom, you can model a country or the whole world or Mars, you can model anything. So let's say this tutor, it has like only 2 options, right, as multiple choice, right, 4 or 3, then there's a 50% chance you can get it correct. So similarly, like, there's some tutor, but it's really confusing, right? So if it's really confusing, even if you know the answer, you only get it 40% correct. So, is it clear up to now? Is there any confusion? If somebody wants to create a model of themselves or their friend, you are please welcome. Okay, so now we are going to model a classroom, right? They are all high knowledge students, you know. So on average, 90%, the students get 90% correct. And let's say there's a classroom that's like a bunch of cheaters. Again, who resonates with that? Who comes from the classroom that's a bunch of cheaters? Okay, this is your model, right? So the thing is, like, even they don't know, right? They cheat and they get it 70% correct. So now this is another model. So there is not only knowledge is going to affect, there's a cheating is also going to affect. And I think this is the model of our SLC examination, our board, 10th grade board examination, right? So yeah. And when you do that, you know, like, this is how your conditional probability table is going to look like. So because knowledge and cheating, they are like independent up to now. So they have the probability table like this. And now performing correct is dependent on both knowledge and cheating. So the more nodes you add, this table gets like exponentially more complex. So how about, again, this is another model, right? So how disciplined you are is going to impact your knowledge and your cheating. Again, like, does anybody want to volunteer making a conditional probability table for this? Okay, so now we just like handcrafted those models, we handcrafted those conditional probability table, right? But the point is like, where do this come from, right? Where do those numbers come from? Because right now I just made it up, but because I have some hunch about the world, but sometimes you don't know about any knowledge about the world. So where do they come from? That's one question. And like once you have that, table, what do you do with it? Okay, this is where the inference in Bayesian network comes from, and the word Bayes comes here. So there's the Bayes bar. So you remember the Bayes equation, right? Okay, so this is the representation. Now we are going to inference. So this table tells us like, hey, we know the knowledge. From that, we can guess what would be the performance would be like. But in real world, we actually see the performance, but we don't know the knowledge, right? So we are more curious about knowing what they know, because the performance we can see. And this is the latent, and this is where this whole Bayesian network inference comes handy. Okay, so this is the equation. So we have this P no from the table, and we P correct, we can actually observe it. And again, this probability we know from the table. This is what we need to deduce, right? So we are going to do this posterior probability calculation from this equation. So what it gives a tool, right? I mean, it gives the relationship between knowledge and performance. Now you have this relationship. So once you know the performance, you can actually guess. Because based on that, right? If your model says that, hey, there's a very high guess rate, then you see the student has done correct, but still you are not sure that the student has the knowledge. Similarly, if your CPT says that there's a high sleep rate, and you might see the student has done incorrect, but still think that, hey, the student might have slipped. So this is how you infer. The same thing, like if you, if this model is based on a class of cheaters, like you don't really trust that they know, like what happened in Pulchok Engineering Campus lab sessions. Okay, so again, this is a dynamic Bayesian network. We don't have to go more into that, but what is saying that sometimes, like, you know their performance right now, but you don't know what they are going to perform in next step, right? And this is where it comes from. So again, so based on this instance, you guess their knowledge, and from that knowledge, you guess their next performance. Does it make sense? Like, you can see how they are performing at present. From that, you can infer what would be their knowledge at present. So now you know what they know at present, and from that, you can guess how they are going to perform next. So this is how you play with this Bayesian inference. So now we did how you represent in Bayesian network. We learned how you infer. The next is like, how do you learn in Bayesian networks? Like, how do you learn those parameters, right? So there are different algorithms: maximum likelihood estimation, expectation maximization, gradient descent, MCMC. There are various algorithms that helps you get those parameters. So now I'm going to give you an example from this knowledge tracing model. This comes from AI in education domain. So what's going on here is, if anything is confusing, again, please raise your hand and ask. So, okay, so you are students, so you can totally understand it. So this is like, you see the student knowledge is going to impact their performance, right? And that knowledge is going to go forward. So that's, what you know now is going to affect what you know in the next instance. So there's a prior knowledge because the student already have some, prior knowledge. And from this thing, these are the parameters, like what is their prior knowledge, what is their guess rate, what is their sleep rate, and what is their learning rate. So this is how it goes. Like I'm talking about this particular instance. So it can be different. Maybe another algorithm might be using MCMC or gradient descent. But in this particular model, this is what's happening. So there's a knowledge tracing model, which is using EM algorithm. And you give them input, performance data, and it's going to give you output of those parameters. Because, okay, this is what happens. Like, you can't tell, what is their guess, what is their sleep, right? All you can see is like how they are performing. So I'm talking about the computer tutor. So do you know what is computer tutor? So it's an educational software, right? So I have this software that students are using. All I can see is like whether they are doing it correct or not. I don't know anything about them. Like whether they are guessing or cheating or sleeping or how much they know before, I don't know anything about that. So this is all I know. So this is the data file. So this student at time A, she didn't get it right. At time B, she got it right. So this is the whole table of sequence of, their performance data. And from that, I feed this data to the knowledge tracing model, and which has this algorithm, the Bayesian inference, and there's the EM algorithm. So it has all this this structure, which is told to this model, and from that it is going to spit out all these parameters. So it is going to fit and get the best fit. So it's going to tell me, hey, your prior, on this data, the prior knowledge is 0.52, learning is 0.09, guess rate is 0.39, and sleep rate is 6.6. So what it is doing is like, after it observes the student data, and then it does some inference, and it tells me that, hey, your students have 52% of knowing it beforehand. They are learning at the rate of 9%. They are guessing at 39%, and their sleep rate is 16%. 16% of the time, they are not getting it correct, even if they know the answer. Is there any confusion here? Okay. I think it has to be on.
So to get prior knowledge and to understand whether they are learning, does system provide new information also? Like if the student got it wrong, then are they presented with new data so that they can learn and get it right next time, or how is it?
Sorry, can you say it again?
So our students are being shown new data once they, if they get something wrong, does the system show something new and then analyze he's learning, or how is it?
Yeah, so how do we turn it? So in intelligent tutoring system, there are two parts. So one is inferring about the student, like knowing, making inference, making guesses about the student state, how much they know, all that. And one is like giving the right feedback, giving the adaptive feedback. There are two parts. So now we are only talking about, we'll get to that. So this part is only like sitting at the back and trying to understand the student. Up to this point, it's not doing anything. It's just trying to, learn about the student. Okay, this is like that. But this knowledge, you can use it for adaptive thing. Okay, I'll go back to this. Like for example here, right? Up to this point, it is only trying to understand the latent knowledge, right? But here, you can use this knowledge to guess what would be the next performance. So based on that information, it can make adaptive or personalized feedback. So this, because at the end this goes to personalization. I think that's what your question is, right? Okay. Yeah. Now we are at this point, right? So after you have these parameters, right? What do you do with this? Because it helps you predict the next performance. Is the student going to get it correct or incorrect, right? So that means if you think that the student is going to get incorrect, you can say that, hey, you might need some help. Do you want to try this, right? Or if you think that the student is going to get it correct, then you offer them more difficult question. So you can change the problem difficulty, or you can offer them help like that. Or if you can see that the student is sleeping a lot, then you can see that, hey, you know, they are called the affective tutor. They also give the emotional feedback. Hey, you look like kind of like, sleeping a lot. Do you want to read the problem more carefully? So based on that parameter, they can give you the adaptive feedback. Okay, so this up to this point, this is really good at predicting what would be like that, right? But do they really help us understand student learning behavior? I mean, of course, we got those parameters, the learning rate, sleep rate, but are they? Can you trust them, right? Are they just fitting, or are they the real values? I think this is one of the very core problem in machine learning and AI, right? So you get those parameters, it helps you predict, but are they real, you know? So because in that knowledge tracing we are using EM, and it has a multiple global maxima. So because it has to start some prior, so based on where you start, right? Because you first, to start training it, you need to give some prior, right? Okay, so the prior knowledge and prior could be confusing, but the prior is like you first set like the knowledge could be, prior knowledge could be 0.5, guess be 0.2, and then it changes. So what happens is like your final parameter estimation is going to be very dependent on your prior setting. So that's one of again the problem we get into again. So this again, don't be confused by the whole this too many thing. But from this, what I'm going to say is because there's a multiple global maxima for the same performance, 3 different knowledge curve is going to fit in that, right? So they might, 3 different students with different knowledge profile might have the same performance. I mean, the student who has very high knowledge but is very prone to sleeping might look like the student doesn't have high knowledge, but they are good at guessing. Is it clear? So because you can't really tell, you know, what is going on, right? You can only guess. So you just have this bunch of performance and you are just like fitting and maybe this is happening because, okay. So you have this performance and you already assume that student has high knowledge, right? Because in the classroom also it happens, right? If a very, a bright student does some mistake, the teacher says, oh, the person might have slipped, right? But if somebody who is not that studious, but if the person gets discarded, the student think that, oh, she might have guessed, you know? So, do you get? So, and it does the same mistake. So you only see this performance. So if you already assume that the prior knowledge is high, you think that, hey, this is a very high knowledge kid, but which is just like very prone to slipping. But if you start with thinking that, hey, the student might be not high knowledge, then if you see this up and down, you say, hey, the student might just be guessing. Up to now, like you see that Bayesian networks are good at prediction. I mean, the parameters are not meaningless, you know, but the thing is that you can't conclude that this is actually happening, you know. Maybe there are like 2 global maxima, maybe there are 3 global maxima. You can only, you know. But it is good at prediction. It will be good, you know, but it will still be compromised at understanding. So that leads us to next topic, that is causality. So up to now, does anybody have any question?
The thing with the performance of students, like slip rate, learning rate. Can you go to that slide? Yeah.
This one?
Yeah. The thing is about prior knowledge. If this system is installed, and how do we know that the person or a student has a prior knowledge? Meaning that what are the base cases that we guess? Like suppose I'm at Coursera, right? I'm giving exam and this system is installed, and everything is based on prior knowledge. So how do we evaluate that the student has a prior knowledge? Yeah, that is the first question.
Yeah. So what happens is like, so do you know this domain already or not, right? So that's why. So they call the certainty factor. Like let's say like I'm going to the new class. I don't know anything about them. Then to be safe, I put all this probability, maybe 0.5%, or which is closer to the mass reality, right? Because sleep rate can't be 90% or guess rate can't be 90%. So I just put some like vague number that might be closer to the bigger reality. But if you already have some like information about the system, then you set the prior accordingly. And also there's a different way of, again, this is one of the very key issues. How do you set the priors, right? So that's why there are different, because again, this AI in education is a very evolving field. And sometimes people use the DD-slip parameters, which actually add the confidence, because sometimes you know that the student might have 50%. You set the prior as prior knowledge as 50% because you don't know. So you just put it as a low confidence, right? But you have worked with the people and you know very well that those students, those classrooms indeed have only 50% chance of knowing, then you give the prior with more confidence. So there's a different way, there's a mechanism you put it. But yeah, this is one of the very tricky thing. Like I think it's very there's a knowledge engineering and there's the machine learning and all this coming along.
So I have one thing I'm a bit confused about. So when you create your graph, right? What you're trying to estimate is the strength between the nodes, right? The weight of the edges, right?
This one?
No, when you just when you do your estimation.
You mean this one? Or which?
For example, whatever graph you're using, okay? When you take the different students, what tells you that the weight of the edges are actually comparable across the students?
Oh, okay. So yeah, that's the thing. So there are two parts, right? So there is the qualitative part, like how are those variables are related, and one is the quantitative part, like in what way, So we all know wherever we go, like this classroom, wherever we know that the knowledge is affected to the performance, right? We at least have this set, and then those variables, like again, you kind of changed. Or am I getting the question?
So, no, I understand how you make the graph qualitatively, and I think I understand what you do when you estimate it. But when you estimate it, you're not estimating one graph per student, right?
No.
So
no, you can do that as well. So you can estimate for anything.
No, I understand that you could do it for every student if you had enough data, but it's very unlikely you will have the data to do that. So when you just have an aggregate of data, how do you know that the relationship between the nodes has the same weights for all the students?
They don't have. It's going to be different.
Okay.
Yeah, so I did one experiment with I have all the data of the performance data, right? And I also know what is their self-discipline because we did a survey. So, and then we actually created 3 different, so we can set the parameter and they make different categories, and for different self-discipline group, they give you different parameters. Yeah, and actually we found that the students who said that, oh, I'm highly self-disciplined, they actually had a higher prior knowledge and higher learning rate. I mean, I don't have it now to show, but yeah, we do it for different group. Yeah. And any more question? Okay, shall we move to the next section? I think it's going to be more fun.